Hey everyone, welcome back to Math 261. This is Scott. Let's get started. Now for the very last installment of Chapter 4, 4.6. And here what we'll discuss is change of bases. So here's the idea. There's a vector space. I have a basis, you have a basis. So I call my vectors one thing, you call them something else. And so how shall we communicate with each other? How can we convert the vectors from one basis to another? So that's the basic idea here. We have a vector space with two different bases. And what we're discussing here primarily applies to finite dimensional vector spaces, but that's really in most of our vector space analysis, that's where we're going to be keeping our attention focused. So we have a vector space V with bases, with two different bases, we'll call them B and C. B for basis, C because it's the next letter. So B, which is made up of vectors B1 up to Bn, and then the other one is C, and you write the script C in that sort of fashion, which is made up of vectors C1 up to Cn. Now, as we already said in the last section, if we have two different bases for the same space, they must actually have the same number of elements. There must be a one-to-one correspondence between the elements of one vector space and the other. Now, if each of these is a separate coordinate system for V, then what that means is that each vector in V can be expressed either as a combination of these elements or as a combination of these elements. So then, for x in V, or I should say for V in V, either way, for each V in V, there are representations V with respect to B and V with respect to C. For each V and V, there are two distinct representations, one relative to one basis, one relative to the other. Now, if we want to try to convert from a representation in one direction to a representation in the other, one way we can do that is through what is called a change of basis matrix. So, it's called a change of basis matrix, and the way we write it is like so. So we write it with a P, and we go from B to C, but we write it from right to left. There's a reason why we write it that way, which you may find a little bit counterintuitive. But this is the matrix that will actually accomplish the transformation between the two different bases. And what this actually means is this. So what we're going to do is we're going to take column 1 to be the representation of basis element 1 from B and express that with respect to C. and then this is one, and then the next one is going to be column 2 of B expressed with respect to C, etc. up to column N. Then, what this would do, if we could ever figure out how to accomplish such a thing, what this would do is give us a recipe for changing from representation with respect to one to the representation with respect to the other. So then, V with respect to C will just be this matrix that we just found, P, from B to C, again written this way, times the vector V with respect to B. Now this is part of the reason why the notation is written this way. It suggests, since we're multiplying by the matrix from the left, it suggests that we're converting it essentially from B via this matrix into C. But how do we actually make this thing? So this would then turn it into just a simple matter of matrix multiplication, if that were to be found. But how do we find it? So finding P. Alright, well, case 1 is where basically we are already told what the recipe for P is, just in sort of indirect form. So case 1. We are explicitly given the representations of the B's with respect to the C's. So then it's just a matter of converting it properly into a matrix. So an example here would be like the following. So we could have B has the two elements B1, B2, and C has two elements, and we know that they always have to have the same number of elements, C1, C2. And we are just given recipes for what B is in terms of C, what each B is. So then B1, so where B1 is equal to like 2 times C1 minus 3 times C2, and B2 is equal to, let's say it's just something like C1 plus 2C2. Okay, so what we've been told is the recipe of the weights on the various C's that go into making each of the B's. But the weights that go on these basis elements to make these basis elements, that is, in other words, the representation of B1 with respect to C. So this means this is just saying 2 times the first element, negative 3 times the second. That's exactly what this representation is supposed to represent. And B2 is going to be 1 times the first element plus 2 times the second element. So then, the matrix that can accomplish any change of coordinates from B to C can be written as follows. So then P from B to C will just be the matrix whose columns are exactly those. So 2, negative 3, and then 1, 2. So that's easy. Then what if we wanted to do something like find representation with respect to C of vector x if the representation with respect to B. Actually, I'm not going to write it that way. I'll write it like this. If x equals 2b1 minus b2. So we can even write it in this sort of recipe, rather than giving it explicitly as a representation. Well, then what that means is that we can find that representation with respect to B by just listing off the weights of the two different components, so 2 and a negative 1, and then the representation with respect to C will just be this matrix 2, negative 3, 1, and 2 times the vector 2, negative 1, which you then just calculate away, and you get 4 minus 1 is 3, and you get negative 6 minus 2 is negative 8. Now, one note about this change basis matrix. If this one goes from B to C, it may not shock you to learn that its inverse does the reverse. So, note. And notice this is square, and it is invertible, and that will actually always be the case. It'll always be square, and it'll always be invertible, because if you can change from one basis to another, you can change from the other to the one. So note, P from, from B to C, inverse, is the same as the matrix that would go the opposite direction. So P from C to B. From C to B. So here, for example, if what we had was P from B to C, I was bad about this, is writing it backwards. If P goes from B to C is equal to 2, negative 3, 1, and 2, we can then just find the inverse of this, and since it's a 2 by 2 matrix, the inverse has a relatively easy recipe. And then what we'll have is the inverse direction. So then this would be 1 over, let's see, so it's the determinant, so 4 plus 3 is 7, and then it's times the typical scrambled up version of the entries here, where you switch around the A and the D, and you make B and C the opposite. So then that would be a 2 and a 2, okay, those didn't switch very much. And then what we're going to have is a negative 1 and a positive 3. And then just because it's always a good idea to check yourself on these things, because it's so easy to make mistakes. If you were to multiply this out, would you get, in fact, the identity? So a quick check. So 2 times 2 plus 1 times 3 equals 7, which will make a 1, which will do it. and then those will cancel out and make a 0. I always want to do that just because I'm always worried in my mind that I'm going to mix up the relatively easy scrambling that happens with a 2x2 matrix just because it's so simple, one gets complacent and can easily make a common error. Okay, so this means, so if I write it as 2/7, -1/7, 3/7, and 2/7, this will be the matrix that goes the other direction. So this is the reverse. Oops, sorry. Then what I meant to say here was P inverse. Is that? So if this is the matrix that takes you from one basis to another, its inverse takes you from the one basis to the other, or the other basis to the one. So there's that. Now that was case 1, where an explicit recipe for the elements of one basis are given with respect to the other. However, but the other case is when we are given the two bases just in their natural form, not relative to each other, but just based on what their actual elements are. So, case 2. B and C are given directly. So for example, what this would look like, just so we know what we're talking about here, we might have a B which equals, let's say we're in R2, 1, 2, -1, 3, something like that. And then maybe the basis C is the two vectors, let's say 4, 0, and then 1, -2. Alright, so what we do not have here in any explicit form is any of these vectors with respect to these or vice versa. What we have instead is just each of the bases kind of standing on its own. So how do we make the matrix here? So making the change of basis matrix from B to C. Now, if we wanted to make the change of basis matrix from C to B, you just do the exact same thing in a swapped orientation. Okay, first recall what just P sub B, what that actually means. We've seen this matrix before. This was called, we even called it a change of basis matrix back then. So this is equal to just B1, B2, and this is the change of basis matrix from B to the standard matrix. Sorry, from B to the standard basis, I should say. Basis. And similarly, for P sub C, which would equal C1 and C2. Now let's think about what this actually means. What this means is that this is the basis that, or this is the matrix that changes from representation with respect to B to the standard basis. In other words, regular format. So what that means is that PB here would be so P just a B, not B towards anything, just B towards the standard matrix or standard basis. I keep saying that. Would be 1, 2, -1, 3. Also, P sub C would be then 4, 0, 1, -2. Now what we want to actually do is, to make the P from B to C, is we actually want to augment one matrix with another. So then, augment the matrices to make P sub C on the left and P sub B on the right, with the bar or not, and row reduce. And if we row reduce here, we'll end up with just getting the identity on this side, and what we'll have on this side will be the desired P from B to C. So this is our desired matrix. Let's see this in action. And then we'll discuss why this is the approach. So then what we'll have, so in the example, what we would be looking at would be a 4, 1, 0, -2 augmented by a 1, 2, -1, 3. Now we just do what we ordinarily do. Once we have augmented a matrix, the next step is almost always to row reduce it, and so you can do this either by hand or by the miracle of technology. And in any case, you will end up with 1, 0, 1/2, 1/8, 0, 1, -1, -3/2. Now, what's the significance of what we have produced? Right here on the right, what we have is the change of basis matrix. So P from B to C then equals 1/2, 1/8, -1, -3/2. So that is the cookbook approach to doing this is just how to do it. But then why? Why is this the correct approach? So let's look at what it is we actually did compared with what we know that this matrix is supposed to represent. So this matrix, its columns are supposed to represent the representations of the elements of B with respect to C. So what we've got right here, this is the recipe to make B1 out of C. B1/2 times C1 plus -1 times C2. And if you look right here, our goal is to make this vector out of these, and it's 1/2 of this one, so that puts it at 2, 0, plus -1 times this one, so that's going to make, so then that's going to make 1 and 2. And so the reason why this works is that what we have done is basically, it's as though we just did two different operations of solving systems of equations. This one was solving to find the entries to make B1 out of C, and then this one was solving to find the entries of B2 out of C, and then we just put them together and we get the recipe for making each of the B's out of each of the C's. So this would be the matrix for P from B to C. If we want, sometimes we do, sometimes we don't, the matrix that goes from from C to B, then what you would just do is you would put the two matrices on the opposite side. So you put P sub B on the left and P sub C on the right. And then we get the identity on the one side, and we'd get the matrix that we wanted on the other. And this is, by the way, the reason why the change of basis matrix is written with such an unusual notation, going from right to left instead of from left to right. It is partly also just to suggest the correct way of doing this. So it actually includes a little hint inside its very DNA for how the process is supposed to be executed. All right. Well, that can pretty much cover that, and we can call it a day. And for that matter, actually even a week. So I'll see you for the next episode of Math 261 after these messages. Bye.